Let's see, I've assigned the next homework assignment, and I'll introduce it here momentarily, just briefly. I posted a lecture video that wrapped up topic 4. And today we're going to start on topic 5. So I wanted to briefly review one portion of topic 4 that was covered in the new lecture video. So topic 4, remember, was all about the multivariate normal. And beginning slide 34 is some discussion of sampling distributions, likelihoods, and the associated maximum likelihood estimators. So I'd like to just kind of underscore this material because it's really important. So a big question in statistics is, how do you estimate the parameters of a probability model? You have some data that are being generated by a random process. A natural question is, can I use a probability model of some kind to represent that mechanism for generating data? If you work at Boeing and you want to know how well your airplanes are going to fit together and last through the upcoming dozens of operations, it would be really handy if you had a probability model that said, for a given age, a given type of plane, a given size, fuel, number of occupants, all these different things. Here's a picture of what I think the probability distribution is for its surviving this week or something like that. If you can write down a probability distribution, a model for a random event, then we can use our data analytic and statistical inference tools to characterize the random process, to estimate parameters for that model, and do inference on them. So a big question then becomes how to estimate and build a model. If I'm trying to estimate the average lifetime of a complete Boeing airplane, for example, then I have in mind a numeric quantitative summary. It's the number of months, say, that the airplane will go without incident before it needs maintenance of some kind. I'd like to estimate that parameter. So if we had infinite resources, we could just run or observe all possible planes of this type. Just keep building them, letting them go until they break. If we kind of investigated the entire, quote, population like that, looked at every single possible plane, then we wouldn't need statistics or statistical inference, because we could just compute, well, for this type of plane, after building a million or an infinite number of them, they last 90.2 weeks on average, and there's no uncertainty. So in statistics, we're stuck with observed data, like a sample of, here's 30 airplanes of this type, and data over the past 5 years. So what we do as in statistical modeling and inference is we postulate a probability model. And depending on the way that we approach that step, that will dictate what methods we use specifically. So you may be aware that in statistics, there's two core competing camps. There's the, quote, frequentists, and there's the Bayesians. These are different ways of thinking about uncertainty and the parameters that govern data that we observe. Frequentist inference, frequentist modeling, and probability thinking it has been the dominant style for the past decades, partly because, in no small part because it's mathematically concise in many cases. If you have such and such probability model, then we can write down at least approximately how to compute a confidence interval and how to compute a p-value, the basic stuff of doing statistical inference. Bayesian modeling is based on Bayes' theorem, and it kind of reorients the way that we think of data and parameters. It's computationally intensive as compared to frequentist statistics. For the more pure Bayesian models, you typically have to write up recursive simulation-like programs that can be very time-consuming and require a lot of computing expertise. But there's I guess a perception, maybe a consensus, that Bayesian modeling is arguably the right way to approach many modern complex problems. And so if I had to guess, I would guess that Bayesian modeling and approaches will continue to get more and more prevalent in modern science. So frequentist versus Bayesian. Likelihoods are a core piece of the frequentist take on modeling and inference. Suppose we have, as we've been saying in topic 4, we have random vectors. Suppose we have a, quote, random sample of random vectors. Random sample just means we have independent draws from the population. Every individual that we sample from the population, we're going to observe p numeric variables for them. x1 is that vector of p numeric variables for the first sampled individual. I have a sample of size n in this case then, x1, x2, ... xn. So these would be n people or animals or plants or whatever we are studying. For each one of them, we have a whole vector of observations. Suppose that we're willing to assume that all of those individuals are independent of each other, statistically independent of one another. Think of it like there's nothing systematically different among these n individuals. They were drawn from the population of all individuals like we're studying in such a way that every single individual had the same chance of being selected. Random sample. That's a core piece of the probabilistic modeling and assumptions that we do for inference, regardless if we're talking frequentist or Bayesian. Unless otherwise specified, we're assuming that all of our individuals are independent of each other. So we have these data, Excel spreadsheet full of numbers, and I would like to ask a statistical question, like what's the average survival time of each of these n Boeing aircraft? For each of the n Boeing aircraft, we might have 100 numeric variables, like how old is this resistor, how thick are these bolts, how many hours of training has the pilot had, ... So I have data, and I would like to characterize what's the average survival time or reliability of maybe each of those components. For each one of the input variables, I'd like to say, how long is that component of the airplane going to last? So one way to approach that is to say, I think I'm going to assume that my data came from a particular distribution. That's a parametric way of setting up a problem. I'm going to parameterize the probabilities that gave rise to my data. In Stats 101 context, you usually have one numeric response variable, like income or average age or whatever. And you might say, I believe that number is a random variable, and it is following a normal distribution. We're doing something similar, except we have multivariate data, and we're saying, suppose it comes from a multivariate normal distribution. If you say that your data represent a random sample from a particular distribution, then what we can do is write down a quantity called the likelihood. Here's what it looks like in the multivariate normal case. Capital L indicating the likelihood. And all it is the product of the PDFs at the n individuals you observed. So in this case, we have a product over the n individuals of multivariate normal where I'm plugging in each of the x's. And it's written generically in terms of mu and capital sigma. Mu and capital sigma are parameters. They're unknown quantities. All we have are the data, x1 through xn. So we're saying, I think my data came from the multivariate normal. If that's the case, then the product of their PDFs, or roughly speaking, the joint probability of seeing my data. If mu and sigma were at any particular value, you tell me what they are, then I can write down a function of them that's, roughly speaking, the joint probability of seeing our data set for that choice of mu and sigma. The likelihood is viewed as a function of the unknown parameters. It's as if, okay, we have seen our data. Conditional on having observed our data, let's think about how likely it would be to have seen our data for a variety of choices of the parameters. Are our data more likely to have come from the multivariate normal with a mean of this mu and a covariance of this capital sigma? Or is there a different choice that makes it more likely you'd have seen your data? So a frequentist way of thinking says, we observe data, let's postulate a probability model, and then let's view the parameters of that model as the argument for this likelihood function. And then maximum likelihood estimation is a general methodology for coming up with, for example, an estimate of mu. What's mu with a hat on top? What's a good estimate of mu? Maximum likelihood estimation says estimate mu as the choice of mu that maximizes the likelihood. Roughly speaking, all we're asking is what value of mu makes it most likely for us to have seen the data we saw. We also have sigma, so we're simultaneously needing to ask what value of sigma together with mu are the most likely set of parameters to have given rise to our data. So maximum likelihood is an optimization problem. You write down a probability model, that translates to a likelihood, and then you want to find mu and sigma, or whatever the parameters are, that maximizes the likelihood. It's an optimization problem. Okay. Skip that. So if we are in that situation that I described, you have n random draws from a multivariate normal distribution, and you want to come up with good estimates of the parameters, mu and capital sigma. These are the maximum likelihood estimators of mu and sigma. Shouldn't be surprising. Mu hat, the best estimate you can get in many ways. The maximum likelihood estimator of mu is the vector of sample averages. So this would be if mu contains 5 variables, it's the average of variable 1, followed by the average of variable 2, average of variable 5, in the population. Those are parameter values. Then my best estimate of those would be collect some data and then report the average, sample average of variable 1, followed by sample average of variable 2, Similarly, my MLE for the covariance matrix, call it sigma with a hat on top, is basically the sample covariance matrix. So let me write a blurb on our whiteboard here. Our initial introduction to an average, x bar, and a covariance matrix estimate, S, went like x bar is let's do, it's the average of variable 1, average of variable 2, sample averages. And the sample covariance matrix was this thing. It was like an average, but a little bit different based on the dividing constant. So that's almost an average. It's add up the product of deviations from the mean, and then divide by not quite the sample size, but the sample size minus 1. And I kind of mentioned or commented on that last week. The reason that we divide by n minus 1 instead of n is a technical one. And in fact, the maximum likelihood estimator of the covariance matrix, see that it's written as n minus 1 times s divided by n. In your notes, you're going to see in some places we say s, and in other places we say Sn. Sn is the MLE. And it turns out in this case that the MLE is not equal to what we usually use as the covariance matrix estimator. So just to put some context on this slide, there's two versions of covariance matrix estimates. If you ask R for the covariance matrix from a data set, it will give you this capital S. The MLE is slightly different. But notice that with big sample sizes, when n is big, they are virtually identical. And in fact, that's why Sn is the MLE. Because the properties of MLEs, what makes them so nice, is that they have large sample asymptotic results. As n goes to infinity, we can say a lot about maximum likelihood estimates. So what I want you to take from this chunk of the topic 4 notes. Number 1, the idea of estimating parameters using likelihoods. We're going to see likelihoods multiple times throughout the class. And it's good for you to know that's a core statistical idea. Likelihood-based inference. In the multivariate normal case, which this whole chapter, that's what it's all about, we have these MLEs. The mean vector is estimated by the sample mean vector. The covariance matrix is estimated by S sub n. That's like the covariance, sample covariance, where we're dividing by n instead of n minus 1. So given data, an Excel spreadsheet, you can now compute a sensible estimate of the mean and a sensible estimate of the covariance matrix. And the other thing that I want you to take away from this chunk that's really core to statistics is that estimates, like these maximum likelihood estimates or any other type of estimate, something that is a statistic, a number or a vector of numbers that you compute based on observed data, is called a statistic. And because your data are obtained randomly, the statistic has a random value. A statistic is itself a random variable. So here's what I'm talking about. If I have a data set, xn, random sample, another way to say that in shorthand is independent and identically distributed. That's just shorthand for, again, random sample. Every individual is independent of one another, and they all came from the same distribution. If they came from some distribution, call it F, with a set of parameters theta. Special case would be when F is the normal. and theta is mu comma sigma. But more generically, some distribution that can be parameterized with the vector theta. Under that setting, we can write down a likelihood. The likelihood of observing our data, viewed as a function of the unknown parameter theta, is of this form. You product up the PDFs evaluated at each of the observed individuals. A product of probabilities is a joint probability when everybody's independent of one another. So this is, again, roughly speaking, because these aren't exactly probabilities, they're PDFs. Roughly speaking, this is a joint probability of seeing all of our data as a function of theta. Then theta hat, the MLE, is the value of theta that maximizes the likelihood. So this is the MLE, and it is a statistic because it's just a number or a vector of numbers that I computed from data. And the important bit here is that any statistic has a distribution. And we call it a sampling distribution, just to emphasize that we're talking about a probability distribution for a sample statistic. Sampling distribution. When it comes to doing statistical inference, computing p-values or confidence intervals, both of those build off of a sampling distribution. I'll say we'll revisit that, but as we go through this class. But for now, suffice it to say, the process of doing statistical inference builds directly off of this idea of sampling distributions. So if you want a p-value or a confidence interval for an arbitrary parameter, you need to estimate that parameter, and then you need the sampling distribution of the estimate. So let that fester in the back burners. We'll revisit the ideas of sampling distributions. But this slide here, I wanted to just revisit briefly. In the multivariate normal setting, we found out what the MLEs are of the mean and the covariance matrix. X bar was the MLE of the mean vector. And what is nice about this slide is that it's saying, here is the sampling distribution for the mean vector. And similarly, we can write down mathematically the sampling distribution of a scaled version of the covariance matrix estimate. This is the type of result or set of results from which we can immediately get p-values and confidence intervals. I have a probability model that's parameterized by a collection of parameters. From that probability model, I can build a likelihood or write down the likelihood. Then my estimates, the MLEs, are just the parameter values that maximize the likelihood. And then to do inference, I can use those MLEs to estimate their corresponding population parameters. But to do inference with a stated level of confidence interval or a p-value, I need the sampling distributions of those statistics, in this case MLEs. One of the nice features of doing likelihood-based inference is that we can often write down analytically, at least approximately, what the sampling distributions of the MLEs are. So likelihood-based inference is a really general way to assign a probability model, get estimates based on data, and put confidence bounds around those estimates. So again, watch the lecture video, and it goes through, I think, everything in the last part of topic 4. Where we're going in topic 5 is really relevant to this, because in topic 5 and then in topic 6, we're going to start doing multivariate statistical inference. First question we're going to ask is, suppose we have multivariate data and there's some mean vector mu. I'd like to estimate and do inference on that mean vector mu. I work at Boeing, and there's a 20 vector of numeric quantities that I want to model probabilistically. So how do you do inference on a single mean vector? If you want to do inference on a single univariate mean, Stat 101 stuff says go look at the t-distribution, for example. Get a t-test to do a hypothesis test. Get a t-based confidence interval for a confidence interval. That t comes from, the reason I like the t in the univariate case is because it's the sampling distribution of the MLE in the univariate case. So we're going to generalize that to saying now I have a mean vector and a corresponding estimate, and I would like to get a p-value or a confidence region for that mean vector. So we're going to see a multivariate generalization of the t-test and a multivariate generalization of the t-based confidence interval in Chapter 5. So let's go ahead and go to Topic 5. I'll open it up real quick. Say again? Over here?
Yeah, the first one.
This right here?
No, that's the second one.
This over here?
There's the slide before that. Yeah, that.
So before I go into the Topic 5 notes, let me just briefly introduce you to Homework 2. So Homework 2, number 1, asks you to go find the maximum likelihood estimates of mu and capital sigma. So you're going to assume that these data, this Excel spreadsheet of data, n by p, each row is an individual, each column is a variable. So you have a sample of size 4, and for each individual you have 2 numeric variables that you're observing. You're going to assume that the x1 vector, comma x2 vector, comma x3, comma x4 vector are a random sample from the multivariate normal, bivariate normal distribution with mean mu and covariance matrix capital sigma. So it's just like the setting that we just reviewed in Topic 4. And then the question is, what's the MLE of the mean vector and what's the MLE of capital sigma? Then I have some distributional questions. If we have a multivariate normal random sample size of 60 from a 6-variate multivariate normal, then tell me the distributions of a few of these quantities. This is relevant to basic multivariate stuff, multivariate normal stuff, as well as sampling distributions. So 1 or 2 of these are sampling distribution questions. 1 or 2 of these are just basic multivariate normal questions. Number 3, in the latter part of Topic 4, I had some material about, suppose you have data, you have an Excel spreadsheet full of multivariate data, and you want to know are your data approximately multivariate normal? Before you go and do multivariate normal-based MLE inference, you want to be confident that your data are defensibly normal. Otherwise, your inference has question marks about it. So a common question would then be, well, do my data look like they could have plausibly come from a normal distribution? So here I'm asking you to investigate that. You can make a plot called a QQ plot, and there are various transformations of the data that you can make to try to wiggle the data around until they do look approximately normal. I want to use normal-based MLE inference, but my data don't look normal. One option would be to try to transform my data to make them be normal. A common way of doing that is with what are called power transformations. Number 4 is multivariate or inference on a mean vector, multivariate t-tests. So go, first of all, evaluate for some real data, the sweat data. When I say the sweat data, I'm referring to data that are on eCampus. So under course content, data, sweat. This will just be a text file or a CSV file. If you need help opening it, getting it loaded into R, just post on the discussion board and I'll help, or one of your colleagues will help. But I want you to get that data into R. You have a sample size of 20, and for each person, which is a healthy female, we have p equal 3 numeric variables. We have a variable called sweat, a variable called sodium, and a variable called potassium. So first, assess, does the multivariate normal assumption appear reasonable? If so, then go do MLE inference, assuming multivariate normal. So I do ask you to do multivariate inference. First, give me a confidence region for the mean vector, mu. That's like an ellipsoid. In 2 dimensions, you're going to tell me an ellipse within which are possible values for mu about which we're 95% confident. We'll say more about what we mean by that soon. Here's a different kind of confidence interval for multivariate stuff, different kind of confidence intervals for multivariate stuff. And then here is a hypothesis test, a multivariate t-test for a null hypothesis about the value of a mean vector. And then number 5 is another data set, again on eCampus. And this will be from the next topic of material. Instead of doing inference on a mean vector, which is topic 5 stuff, this is asking you to do a multivariate ANOVA. ANOVA is all about comparing multiple means. So we're going to start in topic 5 with multivariate inference on a single mean, and then we'll generalize that to the 2-sample case, and we'll generalize further to the 3 or more group case. All right. So let's come over to our notes. Where did they go? Topic 5, inferences about a mean vector. First up is the multivariate version of a t statistic. And we'll start with a review of the univariate case. So this slide is just a reminder of Stat 101 about t-tests and t-based inference. Suppose we have a univariate mean mu, and suppose we want to evaluate and make a confident decision about whether the value of mu equals a hypothesized value. Is this lake full of acidic, unhealthfully acidic water? We could formalize that as what's the average pH in the lake. And then we could formalize our question as, is the average in the lake, call it mu, less than whatever threshold dictates healthy acid or not, 5.0 maybe. Is mu less than 5.0? And I'd like to ask that using only data, because I can't drain the whole lake and evaluate the whole thing, only sampled data from the lake, but I still want to be able to say I'm this confident in my claim. So we're going to create two competing hypotheses in order to answer this question. There's the null hypothesis, and the null is the status quo, or the claim that you would believe prior to somebody showing you evidence to the contrary. This is just a lake, as far as I know. It's a normal lake. There's no reason for me to believe a priori that it's got an acid problem. So before you show me evidence to the contrary, I'm going to believe the null hypothesis, which is that mu is not less than this threshold. For mathematical reasons, you have to pick a single value for the null hypothesis. So instead of, your intuition might say, shouldn't the null be that mu is bigger than mu0? For mathematical reasons, you have to pick a value. And what we do whenever it feels like you want to make it like a composite null, where there's multiple values in there, for example, mu is bigger than mu0, you pick the boundary value. So my null in this case is that mu is equal to the boundary value. And then the research hypothesis, the alternative hypothesis, what I suspect is true and what I'm going to look for evidence to support within the data is that mu is in the other direction. So there's different types of null and alternative hypotheses. One type is to say the null is mu is equal to mu0, and the alternative is that mu is not equal to mu0. It either is this or it is not that. There's also a one-sided alternative, and in the acid-water case, that's what would be more applicable. You would say the null is that mu equals the threshold, and the alternative is that mu is less than the threshold, that there is acidic problems with the lake. We suspect that, so we're going to collect data and ask, do the data support that claim? But to do inference with in the form of a formal decision, we do hypothesis testing in statistics, in frequentist statistics. So that means breaking my question into two hypotheses, the null and the alternative. Then what we do is observe data. So I go around to 100 locations throughout the lake, and I take a little sample of water, for example. And I assay each one of those for an estimated pH. So I have pH from sample 1 to ... 100. Then what you want to do with your observed data is ask, how different are my data from what I would expect them to look like if the null hypothesis were true? Hypothesis testing from a frequentist angle proceeds by, think of like the legal system. I'm going to assume you're innocent until somebody proves to me otherwise. We are going to assume the null hypothesis until we see evidence strong enough to reject that assumption. So what we need to compute is a number that quantifies how different are our data from the null assumption. In the univariate case, a natural way to do this is with the t-statistic. The t-statistic is sample average minus the null mean divided by this quantity. Another way of writing that in the univariate case, we have x1, x2, xn, and let's say they are a random sample from a normal mu sigma squared distribution. I want to consider the null hypothesis that mu equals mu 0 versus the alternative hypothesis, let's say that mu is not equal to mu 0. What I do in order to quantify, again, the protocol is assume the null hypothesis is true and ask of the data, did you plausibly come from the distribution that would hold if the null hypothesis were true? Are my observed data likely if my assumed null hypothesis is true? So we want to ask the question, if the null is true, how likely are we to see data like ours? And we take a step in that direction by quantifying how different our observed data is from the assumption of the null hypothesis. And it's a t-statistic. This is of the form estimate, as in my estimate of the parameter of interest. My parameter of interest in this case is mu. What's the average is what I'm trying to do inference on. What's my estimate of the average? It's the sample average, x bar. So it's of the form, estimate the parameter, subtract off what you think it is under the null hypothesis, and then divide by the standard deviation of your estimate. S over the square root of n is the estimated standard deviation of a sample mean. And this form for a test statistic shows up a lot. Whether you're testing means or proportions or differences of means or differences of proportions, many times a frequentist test statistic is estimate minus null value divided by SD of estimate. And if you think about what that's doing, that's taking a difference between the estimated mean, your sample mean, and what you think the mean is under the null hypothesis. And then it's scaling that by the estimated SD of your mean. So this is like how many standard deviations away from the null mean was our mean. How many standard deviations from the null hypothesized mean was our observed sample mean? And if you think about normal distributions, we can start to move towards a probabilistic statement of confidence. If you go out 2 standard deviations from the mean in the normal, you capture 95% approximately of the distribution. If you go out 3 standard deviations, it's 99.7%. So we can ask, how confident do we want to be? And if my observed mean is 5 standard deviations away from the null mean, I can say that's extremely unlikely for a normal random variable. And in fact, I can quantify just how unlikely it is with a p-value, a probability estimate. So the t-statistic in Stats 101 is just a quantification of how different our data were from what we would expect them to look like if the null were true. Inference, from a frequentist perspective, is all about sampling distributions. And so in the univariate case, when the null hypothesis is true, so if our assumption of the null is true, then we know analytically the sampling distribution of this statistic. It's a t distribution with n minus 1 degrees of freedom. So if my observed value of t is extreme for this distribution, then I have kind of roundabout evidence to reject the original assumption that I made, which was that the null hypothesis is true. I started out, let's assume the null is true. Given that my data came from a normal distribution, a sensible way to quantify how different they are from the null distribution is to compute the number of standard deviations away from the null mean. And then again, by virtue of assuming a normal distribution, I can say that my test statistic, if the null is true, follows a predictable distribution. So if my statistic is sufficiently far out in the tails, then that says you probably made the wrong assumption when you assumed that the null was true. Or in other words, your statistic is probably not really a t n minus 1 degree, random variable. And that's indirect evidence that you assumed the wrong thing. So if your test statistic, it looks extremely unlikely to have been observed, then you reject the null hypothesis. All right, we're about out of time. But compare slide 4 and 5 to slide 6 and 7. Slide 4 and 5 is a review of the frequentist normal-based inference for a mean. T-tests, and then T-based confidence intervals. And then that's immediately followed by a pretty straightforward generalization of all that stuff. We take a univariate T statistic and we generalize it to a multivariate T statistic. This also is like a deviation from the expected mean scaled by a standard deviation of our estimate. It's more like a squared T statistic than the original univariate T statistic. That's why it's called T squared. But assuming multivariate normality with an MLE x bar and a sample covariance matrix S, this is the multivariate generalization of the T statistic. So we compute this, and then we need to ask, what's the sampling distribution of my statistic? 2 slides ago, if the null hypothesis were true, the statistic was a T random variable with n minus 1 degrees of freedom. In multivariate case, if the null is true, it's a little different. T squared is this messy looking scaled version of an F random variable. But from there, inference proceeds virtually identically. You compute a p-value in the exact same way for a multivariate test as you do a univariate test. And then what's going to get complicated a little bit is generalizing the confidence intervals. In the univariate case, it makes good sense to collect some data and put together a plus or minus, an estimated mean plus or minus, about which we say I'm 95% confident that this particular interval contains the true parameter value. But in the multivariate case, you have more than one mean. So what do you want as a confidence thing? Do you want a single confidence ellipsoid about which you can say I'm 95% confident the mean vector is in there? Or do you want separate confidence statements for each of the component means? And if you want separate confidence statements, how do you want to gauge and control the confidence level? So we'll meet both confidence ellipsoids, and we'll also get into what are called simultaneous confidence intervals
which are appropriate when you have p variables, p means, and you want a separate 95% confidence interval for every one of them. Because of the multiple testing issues, you have to be careful about how you do that. So we'll construct carefully intervals for each of the mean components so that we can say at the end of that, I'm 95% confident that every one of those contain their target parameter. Okay, so that's topic 5, all about one mean vector. We'll continue with that on Wednesday. And then from topic 5, we go to topic 6. It'll be very similar conceptually. The difference is we're going to go from talking about one mean vector to comparing two mean vectors, and eventually comparing more than two mean vectors. Okay, thank you.